Hey there, Chem Squad. This video is intended to help you guys figure out the Chatelier's principle a little bit more. At this point, I would have already gone through some of the basics of the Chatelier's principle, but I think for some of you guys, you might need to see more of a visual process. So let's take a look at a pretty common type of equilibrium system. So remember, an equilibrium system is just a equilibrium reaction that's happening inside a closed vessel. So in this particular reaction, we have iron ions, we have SCN negative ions to form a product, which is FeSCN2+. Okay. Now, because they're all aqueous, we know that we actually have a fair number of Fe3+ ions in solution. So I'm just going to draw a couple of them in like this, just to show that these ions are present in solution. Okay, and because this is a system at equilibrium, we also have some of the product in solution as well. So here you have SCN2+, I'll put another one down here, FeSCN2+. Okay, so in our system, we're just assuming that we can remove the stopper anytime to open or close it as we please. So right now, we have a system at equilibrium. If we were to stopper it right here, the reaction will not change colors at all. It will stay whatever it is. And whatever concentrations of ions that we have, that's what we have. Okay? There's going to be no further changes. However, every time we disrupt the system, we have to add some kind of stress. So let's suppose that we wanted to add more reactants. Now, it doesn't matter if I add more Fe3+ ions, or if I just add more SCN ions, or perhaps I just add both. Okay, so in red, if I decide to add more Fe3+ ions, okay, and I add maybe some SCN ions as well, okay, these extra ions upset the balance of our equilibrium. So I often use a balance beam as a way to figure out which side is upset by the balance. Okay, so right now, if it's perfectly level, it's at equilibrium. But if I added more reactants, obviously this side is going to tilt downwards and this side is going to tilt up. So in order to fix this, what will we need? Well, we need to create more product. Okay? The only way to create more product is for those reactants to combine and form the products. So here are some Fe and SCN. Okay? Here are some Fe and SCN. These will combine to make more FeSCN2+. Okay? So it makes more FeSCN2+. So in the end, I'm going to have more products than before. Okay? But it's necessary for that to happen so that I get this balance again between my reactants and products. Okay? But the concentration doesn't have to be equal anymore. Okay? Whatever the concentration is now, we actually have an increase by the time we reach equilibrium again. So that's why, for this particular example, increasing the amount of reactants, okay, so increasing reactant concentration, causes a shift to make more products. Therefore, by the time we get to the new equilibrium, therefore at the new equilibrium, the concentration of your products increase. Okay, so the shift that's happening right now is shifting towards the product side. Okay, because we're trying to make more products here to use up the extra reactants that we've put in. So the shift is to the product side. Okay. Now, if we take a look at a slightly different example, okay, same kind of scenario, we still have the same equilibrium, but instead of adding more reactants or even adding more products, what if we remove them? Okay, so the stress in this case is removing the products as they form. So the products is FeSCN. So let's assume that we have an equilibrium here that's been established. Okay, if I take away FeSCN, okay, I'm getting rid of it from the solution. My balance between reactants and products will now change. Okay, it was at equilibrium, but because I'm taking this away, okay, this is what I see happening to the balance beam. Okay, if I take away products, I'm going to have fewer products on the product side. Okay, it's unbalanced. So again, the question is, how do I get it back to equilibrium? Well, if I'm removing products, the reaction itself will want to create more products to replace what I'm removing. So again, it's going to try and want to make more and more products so that this side will go back down. So what ends up happening is all my reactants that are in solution right now, they're going to combine with each other to form more products. Okay, all of my reactants that are present will try and make more products. So in the end, by the time equilibrium is now reestablished, okay, at the new equilibrium, we now have an increase in our product concentration. Okay, this is because the reaction shifted again to the product side. So when we remove products as they form, the reaction shifts to the product side to replace the missing FeSCN2+. Okay, and as a result, you actually get more FeSCN2+ being made. Okay, so that's one way of producing more products without adding more reactants. Okay, we rely on equilibrium to do the job for us. Okay, so finally, I have one more example here. Okay. This one's a little different from the others, but it still works on the same idea. Okay, so on this little beaker, on this little flask here, we have our ions again, right? So we have our reactant ions, Fe3+, SCN negative, and we also have at least one product here to represent the products. Now, this time around, the stress is adding something, but you're not just adding Fe plus or SCN. Okay, so we're not adding the reactants. We're adding a different substance. We're adding iron 3 oxide. So the key to this is we have to figure out what kind of ions are being made from iron 3 oxide. So if we take a look at this, this actually splits up or dissociates into Fe ions with a 3 plus charge, as well as O2 ions with a negative 2 charge. Okay. Now, if you look at the O2 ions, so let's add it in. So if we put in iron 3 oxide in here, you're going to be adding in Fe3 plus ions like this, but you're also adding in O2 negative ions like this. Okay. Now, the funny thing is, because we're adding in a substance that contains iron 3 plus ions, this is actually now known as a common ion to our equilibrium. Okay. So if an ion from another substance matches one of the ions that's in our equilibrium system, we call it a common ion. Okay. So by adding Fe2O3, we're actually increasing the amount of common ions of Fe. So this is like increasing the concentration of your Fe3 plus ions, which is the reactant. So what's going to happen when this happens? Well, these extra F3 plus ions will want to react with the SCN ions to make more product. Okay. So it makes more FeSCN2 plus product. Now that's fine, okay, because what this is going to do is it's going to cause a shift to the product side, and therefore you're making more of that product. Now, what happens with the oxygens? Well, the oxygens don't really do much. Okay, these oxygens just end up being spectators. Okay, they will probably react with the Fe plus to just reform some of the Fe2O3 that we've added in, but other than that, these ions have no function, because in the actual equilibrium system that we started off with, there's no O2 negative. Okay, there's no oxygen ion. So if it's not present in the system, it has no effect overall on the system itself. Okay, so that's why they're called spectators right now, or acting as spectator ions. So in this example here, this is kind of like what we call the common ion effect. Okay, if we have a similar ion as one of the substances in our equilibrium system, it will just act to increase that particular substance. So if we were to look at which way the reaction would have shifted in this case, by adding Fe2O3, this causes a shift to the product side. Okay, and therefore creating more products. So hopefully the visuals here are a little bit helpful. You can rewatch this video as many times as you want, but in the end, if there is something that you don't really understand still, please make sure you do email me or ask me when you see me in class. I'd be happy to help you guys out. All right, see you guys soon.